Hey everyone, welcome back to another video. This time let's go through a couple of past problems from codejam round 2. So there's some pretty interesting problems there, and with round 2 coming up this weekend, why not do a little bit of practice this weekend? So this one is called Retelling, and essentially we've got an artistic installment, which is a tiled kitchen floor that can be retiled into different patterns. And so given the existing tile pattern and a new tile pattern, what is the cheapest way to move the tiles around to get the new pattern that we desire? So the floor consists of a matrix of R rows and C columns of square tiles, and each tile is reversible, so one side is magenta and the other one is green. So there's two operations we're allowed. We can flip a tile, which has a certain flipping cost associated with it, or we can swap two adjacent tiles, which has a swapping cost associated with it. So you can call those costs F and S. And so you're given the current state of the floor and you're given the new state of the floor, and you need to find the minimum amount of coins you need to spend to achieve your goal. Cool. And then they've got an example down here. So we're given one board, which is magenta, green, and then the second row is magenta, green, and so on. And then this is what we need to turn it into. And here it's just saying it's a 2x4 board, and this is the flipping cost and the swapping cost, I think. So here's the example down here, and you can see in the first step they've just moved this green tile one to the left to put it here, and then they've moved this green tile across one, and then they've flipped this bottom one to get magenta. So you can only swap horizontally or vertically. And so we've got 100 test cases, and the boards are quite small, so it's only a 10x10 board, so 100 different cells. And so for me, I kind of immediately can just see this as a flow problem. So it's I think this is reasonably straightforward to know what to do if you've ever done flow problems before. But yeah, so why is it not dynamic programming or greedy or something like that? Well, if we think of a large board and trying to do dynamic programming, let's say we're looking at a subsection of the board like the bottom right, and we're trying to solve for that, and trying to dynamically solve like subproblems and reuse those computations. The problem with that is there could be some cell far away on the other side of the board that needs to swap into that sub area, and so things are kind of, we need to look at things globally because everything kind of affects everything else, and we can't just greedily do things because there's no way of just seeing two tiles and knowing that we should just move one tile eventually over to one other location. Because I mean, let's say I'm a particular tile and I want to move to a location to my right, which is the closest location where the tile of my type is needed. Well, potentially there could be someone to my left that also needs to move to the right, so maybe I should go further to the right to give them room to take that spot. So it's like greedy won't work, where whereas it just kind of makes sense, like everything's kind of affecting everything. So if we want to move a tile to a particular location and some other tile is already wanting to move to that location, we need to find somewhere else for that tile to go. And so that feels like a flow problem where we're kind of pushing flows around. So I'll just draw this out. So I've got one grid here, and this is the grid we want to turn it into. So I'll just call that grid 1 and grid 2. And then we've got a tile within that grid. And let's say in the final version we want that over there. We can think of it traveling, well, we could think of it traveling, like this, but really we're assigning that cell to this cell in the final board. So we can call this cell ij and call this cell I2, J2, that's it. And we know, like, let's just say it's a magenta cell and all the cells in between are green. Then we know the cost to move it will just be the distance between these two cells multiplied by the cost of a swap. But what would happen if there was a magenta cell in between the two and it ran into a magenta cell? Well, there's no point of it running into a magenta cell, because if those two paths crossed, then it would be more expensive. Like if it ran into a magenta cell, that magenta cell would be wanting to go further in the same direction. Because as we're kind of flowing things outwards, it doesn't really make sense to have things crossing over. And so, yeah, I think that's one of the insights, is knowing you just want to look at the distance. And let's also draw that cell up here. So this is I2, J2, and this is IJ. Maybe I'll just type that out. And I2, J2. So this is, each cell is connected to every other cell kind of thing. And so we can put a source node and a sink node. And this is kind of looking like a bipartite matching, where we're connecting to every original cell, and then we're flowing out to a sink. And so we can just get the maximum flow from the source to the sink. But we also have a cost with each of these edges, which will be the distance from IJ to I2, J2. Or potentially we could use flips instead of swapping. And that means we'd need to look at, is this cell currently correct? So we'd need to compare this cell with this cell. If they're different, then we'd have to do one flip to make this one correct. And then we'd also need to do one flip to make this one correct, or maybe not, depending on if this one was the same as this one. So the cost would be, I'll write that, cost equals min flipping cost versus swapping cost. And the swapping cost is just the distance multiplied by how much a swap cost. And then this one would have a cost as well, and so on. So the number of nodes will be, well, it's 10 times 10. Well, let's just say R times C times 2, because each node is twice. Plus we've got the start and the end node, so plus 2. So the number of nodes, and then the number of edges will be, so each node, the source has R times C, and the sink has R times C as well, so that's times 2. Plus we have R times C squared, because every cell has to have an edge to every other cell, because it can also potentially map to itself if a cell stays still, for example. And so the number of edges in the worst case will be 202. And so yeah, that's enough to do like an n-cubed solution, which means yeah, we can kind of do a flow solution or Hungarian algorithm or something like that. So it's not quite a bipartite matching because these costs aren't of one. It's actually, I think it's called a maximum bipartite matching. So basically we need to have, every cell has to match to another cell. So we know the flow has to be R times C from the source and into the sink. And with that maximum flow, we need to minimize our cost. So we want the minimum cost maximum flow. So we could use multi-commodity flow as well. And there's this library which I've referred to a few times. They've got some graph algorithms. So they've got minimum cost flow. So usually I go for this maximum flow one. And I mean, we could just flow each of the edges in order by cost, and then something can only swap out a pairing if it, I won't get too much into the details of how this works. I'll link to a good tutorial about this kind of stuff. But yeah, so let's just use this. So grab the raw file. So I think we're ready to start coding. So I'll paste that in down the bottom. So I don't need this test. Actually, I don't need this whole testing module. But it kind of shows you how to use it. So we'll create a new minimum cost solver and so on. We can refer back to the GitHub if we need to know how to use it. And get rid of this whole test module. And I think it's complaining we don't have a main method. So I've got some boilerplate code which I'll paste in. Let's get the input. So they got two samples, which is nice. We'll just test it with this one first. One problem I should have mentioned is if we match this cell to this cell, and we also match this cell to this cell, well, swapping I2 J2 with IJ is the same as swapping IJ with I2 J2. So our cost will be, our answer is going to be double what the actual answer should be, so we need to divide by 2 at the end. Okay. And RC, F, and S. Okay. So we've got R, C, F, and S. Okay. And we want to scan the grid, which is some chars, I guess. But I think I'd rather just use Boolean values, like true or false. So I'm going to make a little, we've got this chars method for getting the chars on each line, but I'm going to make a little helper function. And so we're going to map these chars to true or false. So I'll type it up here first. grid 1. Well, just G1. So if we go, so we need push, and then, and we don't want chars. We want to map those chars from char. Actually, this is in a vector getting returned from that, so we actually need to iterate that, which means we get a reference to a character, so we dereference that, and we'll just say char is equal to m, let's say magenta. So now we've just got true or false. Okay. And now we need to do the same thing again for grid 2. But since this is just practice, why don't we make a helper method that does this for us? So it will need to know how many rows there are, and it will need to know this closure function. So we could just go char to bool. I'll just make a reference to that. So grid, so it'll be a certain type. Our type is Boolean, which is what we want as our output, and we'll have a function which maps a char to a Boolean, and we need to take the row count, which is new size, and it's going to go to a vector of type t, which is our Boolean. So that's, and just for efficiency, we'll go with capacity. And we need to return that grid. So grid.push. And instead of using this hard-coded closure, we'll use the closure that's passed in. So we need to pass a closure. So that'll just be f, which is of type f, which is our closure. But we need to tell Rust that it's a closure, I think. And instead of SC, we'll just go. So we'll just copy what the other ones are doing. So then we can just go self.chars use of move value. So this is a reference to f. And f needs to implement a function of type t, which is, of type char, going to a bool. Sorry, to type t. And what's wrong with this? Reference to a char. So this is taking a char, not a reference to a char. So we need to go into it. So when we consume these characters, we get each character itself rather than a reference to the character, which then can be owned by this function, which can then output a Boolean, and we no longer need those characters. So now why is this complaining? Oh, we need to collect this now we should be good. So I probably wouldn't recommend doing this in a contest, but it's a bit of fun practicing and making a helper function. So now what's wrong with this? Spigner's signature function char to underscore. Really? What did I put here? Yeah. I've seen something similar to this before, so I'll just see how they did it. Using this Finwick tree, I think. So they've got a function that goes to a type T. Figure like this. Yeah, of course. There we go. So I had Etsy. So I was passing in a reference when actually I just want to pass in a character because I've dereferenced the character to make it easier. Okay, that makes a bit more sense. And I do wonder if maybe I should have left it as a reference. But the intent here is to no longer need the original. Character. But maybe I should leave myself that option. So actually, I will make it like that. I think that might be a bit better. So now Let's make a reference to a char. Just means here we need a star. We can still do reference. Okay. Yeah, I think that's a bit better. So this is why you just copy and paste when you try to make reusable code. It's always harder than you expect. Okay. I think if I was using Rust in my day job more, this kind of stuff would be a lot easier. Okay, so now we've got our grids. Now you want to iterate through all the pairs. So we could use flat map. Which is, it flattens an iterator into its iterator and things like that. So we could use that to flatten all of this into just one for loop instead of having nested for loops, but I don't think it matters too much. We already spent enough time doing this. So now we need to, I guess we need a graph so that we can add edges to the graph. So it'll be like what is this library we got called? Prime Jewel. That's the name of the module. And we need the number of nodes, which is times c times 2 plus 2. So we'll let the source node, I'll call it start, be node 0, and we'll let end equal 1, let's just say. So we'll use the rest of the r times c times 2 nodes for the cells. So answer will be solver dot solve. So we need the source, which is start to end, and the flow was r times c. Okay. And I found floor. So floor is an I64. And we could change this to like U64 or something if we wanted. We'll just keep this as an I64 because potentially it could be big, I don't know. Let's just go as I64. I'm not sure why this is complaining. So this is an optional I64 because, you know, potentially there could be no solution. However, we know there's always going to be a solution. So we can just go unwrap. Okay, so now we just need to let node 1 equal something, let node 2 equal something. So solver.add edge from node 1 to node 2. The capacity will be 1, and the cost will be cost. So we've got the r times c squared edges. We also need the edges going into this from the start to a node and from the out node to the sink. So so we can just do that here. Where can we do this? Should do it here. No, we'll do it. Yeah, we'll do it here. Might be nice if we just do it separately. Separation of concerns, you know. So I don't know what these are yet, but let's just see. From the start to the node, capacity 1, and the cost will be 0. And then from the node to the end. So what is this? We already used 0 and 1 for the start and the end. So we'll have 2 plus r times c. No, we'll have j plus r times c. So that should be a unique hash for that. And then here, for the out node, we'll have plus r times c. To make sure none of these are the same as these. So this node flows into this node. Okay. So it's complaining that I is not used, so that doesn't seem good. And I've made a mistake here. This should be I times c. So the maximum value of this would be r times c minus 1, which is good. So that is node 1. So now all that's left is to work out this cost. Oh, and I should be using I2, J2. So this is wrong. Okay. So now we have a range of IDs for. So this is 0, this is 1. All these nodes are from 2 to r times c plus 2 minus 1 inclusive. And then the next r times c nodes will go, IDs will go to these ones. So now we need to work out the cost. So let's just do the flip cost first because that's probably easier. So it's 0 if they're already both correct. If grid 1 ij is not equal to grid 2 ij, then that means this cell and this cell are different. It means we have the flip cost will plus equal the flip cost. Which I've got here. Just want to make sure I got those the right way around. Yep, the flip cost is first. Okay. And if the other cell is incorrect, then we'll have that cost again. And then the swap cost. So we should only let the cost should just be equal to the flip cost. But then if the swap cost is possible, if we can swap our way between the nodes, then maybe it's better to swap instead of flip. So when can we swap? If this node is wrong and this node is wrong. So if they're both wrong, then this should be true. If they both could have been flipped, then why not just swap them? And it'll be let's just call this swap cost. I'll see if I can create a variable for this. A local variable. I'm trying to make a variable. I don't know. I don't know the shortcut for refactor introduce variable. That's trying to do it for the whole thing. Refactor introduce variable. There we go. No, that's not what I want to do. Anyway, I'll just type it. So swap cost equal the distance times s, which was our swap cost up here. And I guess these might need to be I64s, since that's what our floor library is using. Yeah. So now we need this distance. The distance between the cells is just this. Okay, so I think we are done. Why is this complaining? If once is not general enough. Closure with signature if in. That wasn't complaining before, I don't think. I'm just going to change it back. was complaining that it could get cold twice or something. Okay, so let's see if this works. Oh, the one last thing I forgot to do was to divide by 2. Because now matching every cell goes to another cell. Which means we need to divide by 2. Okay. Oops. So this is not good. First, we'll change the name of this since it wants us to use snapcase. All good programmers use the correct style guide based on the language. Okay. So this is not good, so we've got a hard to find bug somewhere. And the flow should be R times C. Okay. Let's print out the grid and see what it looks like. Grid 2. True, false, true. Oh, that's good. Start cursor node. Looks good. By the way, this would be wrong if the flip cursor was 0, right? Just want to make sure it can't be 0. No, that's good. I see. So this is wrong because potentially if we were to, just because we want to flip both of these doesn't mean we want to swap. We could have 2 green ones and we need 2 magenta ones. So then we can flip both of them, but would never want to swap them. So that's what happens when you try to take shortcuts. You make mistakes, so let's calculate it correctly. Okay, so if G1 I J is equal to G2 I2 J2, that means, we want this tile to move to that new location because that's what we want in the end. And then also, hey, that will be out in a sec. Almost finished this video. And if, on the other hand, this tile is also what we want in the other spot. So this is the condition we need if we want to swap the two tiles. And this should also be a C. So that's a typo. So now let's try that. Cool, 3 and 4. Let's see what we wanted. 3 and 4. And we'll try this test case. Yep. So that's what we wanted. So let's try to submit this. Alright, so hopefully this should run pretty quick, but let's see. And great, so that's the right answer. So that was quite a fun problem. I think once you know the approach, the implementation is reasonably straightforward, although it's easy to make a typo or make a little mistake with some of these edge cases. But yeah, I thought that was quite a fun problem. So let's hope they ask a flow problem next weekend. Alrighty, I better get going.